Okay, we're on top of page 6 right now. The topic is atomic concepts, atomic structure, whatever you want to call it. And you're going to need a periodic table in hand. Most of the information is going to come from the key here as your guide. And let's just get started. The subatomic particles are the protons, the electrons, and the neutrons. They make up atoms. And you can remember it as just PEN, your pen. And these particles differ in charge, whether they're positive, negative, or neutral, mass, how much they weigh, if you will, and their location in an atom. A proton has a positive 1 charge, an electron a negative 1 charge, and a neutron, as you can tell from the name, has no charge. It is neutral. So protons and electrons have the same amount of charge. Notice 1 and 1, just they're opposite in sign. So maybe that's something you want to emphasize there. On the other hand, when it comes to mass, protons and electrons are very different. Protons weigh much more than electrons. On an AMU scale, which stands for atomic mass unit, a proton is 1 AMU to 1 significant figure. An electron is 1 over 1836 AMUs, which means electrons are much, much smaller than protons in mass. Another way of saying this is you would need 1836 or 37, depending on whose book you read, electrons to make up the mass of a proton. And neutrons, on the other hand, have the same amount of mass as protons. So maybe we want to emphasize that neutrons and protons have the same amount of mass. And you can think of electrons as having negligible mass, or practically 0 mass. When it comes to location, protons and neutrons make up the nucleus, or the center of an atom. Electrons are found outside the nucleus in the orbits. So it's for that reason that protons and neutrons are referred to as nucleons, because they make up the nucleus. Something that a lot of students find confusing is when you're asked the charge of a nucleus. Well, the nucleus is the center of the atom. Since that center is made up of protons and neutrons have no charge, the charge of the nucleus is due to the number of protons. So an atom that has, for example, carbon, which will be our key element, an atom who has 6 protons, and the way I know that is from the atomic number. The atomic number is the number of protons. An atom that has 6 protons has a nuclear charge of positive 6. An atom with 7 protons, for example, nitrogen to the right of carbon, would have a nuclear charge of positive 7, or 7 positives, and so on. So the nuclear charge is simply the number of protons, or charge of the nucleus. So this is also known as the nuclear charge. Now, let's see how we can get the PEN, the pen for any atom. Beginning with the key element carbon up on top, you'll notice that the atomic mass of carbon is 12.011 AMUs. Now that is an average, or a weighted average atomic mass. If you wanted to get the mass number of the most common isotope of carbon, and we'll talk about isotopes in a second, what you do is you take this 12.011 and you round it off to the nearest whole number, and that's why I've crossed it out like this. That number, of course, becomes 12. What you now have is no longer an atomic mass, but a mass number. And that would be the mass number of the most common isotope of the element. So, of most common isotope. And we'll talk about isotopes in a second. Think of it as the most common form of carbon. Okay, now that mass number represents a total. total of protons and neutrons together. So it's the sum of the nucleons, if you will. So the math is very simple. All right. If we know the number of protons and neutrons together, if we subtract the number of protons from that, we would get the number of neutrons. So it's the top number minus the bottom number. The mass number minus the atomic number gives us the number of neutrons. Now, in the case of carbon also, we want to note, and for any atom that's neutral, the number of protons is the same as the number of electrons. The atomic number, once again, first, above all, gives us the number of protons. In a neutral atom, that's equal to the number of electrons. To get the number of neutrons, we round off the atomic mass to the nearest whole number. It becomes a mass number. Top number minus the bottom number gives us the number of neutrons. Let's put that in here. In a neutral atom, number of protons is equal to the number of electrons, since the positives and negatives will cancel. Now let's practice getting a pen for a number of elements. And in your notes there, which again you have a filled out version, I decided to do 3 elements. And that is, let's begin with aluminum. Look up aluminum, Al. If you don't know the symbol of aluminum, you could always refer to table S. Aluminum is number 13. So that 13 right away tells us, let's practice together, 13 protons, 13 electrons. It's a neutral atom. If it were a charged atom, an ion, then you'd have a charge up here, and we'll deal with that in a second. Then, its atomic mass is 26.98154. Let me just move this cursor here. So it's 26.98154. Well, to the nearest whole number, that 26.9, the 9 makes that 6 or 7. So we'll make that 27. And 27 minus 13 is 14 neutrons. So that would be the most common isotope of aluminum. Next, another element to practice with, and why don't you do this with me, is potassium. Now, potassium is not letter P, that is phosphorus. Potassium is the letter K. Look at potassium, which is element number 19. Let's do it together. 19 protons, 19 electrons, and 39.0983 becomes simply 39. 39 minus 19 is 20 neutrons. All right, let's try one more element. Why don't you go to now tin. And tin is not Tn. Tin, if you look it up at table S, would be Sn. And tin, you'll find it as element number 50. So again, tin has 50 protons, 50 electrons. Then the mass, the atomic mass here is 118.71. So we'll round that off to 119. 119 minus 50 is 69 neutrons. Okay, simple math. You always use a calculator. Let's move on to the next part of the page. Once you get your pen, the next thing to cover in atomic concepts is this thing about isotopes, which confuses a lot of students. I guess they confuse isotopes with isomers. Isomers comes up in the organic unit. That's when you have the same composition, the same formula, but a different structure. But isotopes is when you have the same element, atoms of the same element, that differ in the number of neutrons. So let's look at that together right now. So the isotopes, by definition, are atoms of the same element. So it's the same element, which differ in the number of neutrons. And because of that, isotopes are going to have the same atomic number, but a different mass number. Remember, the atomic number is the bottom number. The mass number would be the isotopic mass in this case, rounded off to the nearest whole. So here's carbon-12, the most common isotope of carbon, and carbon-13, 0.00335. The abbreviation would be C-12 and C-13. That doesn't mean C with a negative charge of 12. It's just a shorthand abbreviation of rounding up this isotopic mass to 12. Rounding off this isotopic mass to 13. Again, notice how both of these isotopes, and of course you would be given this information, you'll notice that neither of these is the weighted average atomic mass that's listed in the table. Neither of these is 12.011. Because we're going to have to do a little math to get to 12.011. Notice how they both have the same number of electrons. And now the neutrons. 12 minus 6, 6 neutrons, and 13 minus 6, 7 neutrons. There's your key difference. So again, notice how the isotopes differ in the number of neutrons, and because of that, they will have different mass numbers. Now, if you're given the percentages of each of these isotopes, then you could do a weighted average. So if you're given that, the relative abundance, or the percent relative abundance, that's how much there is percentage-wise of each isotope, is of carbon-12, 98.89, and carbon-13, 1.11, then we could use that information. So let's take these percentages here and calculate what is called a weighted average atomic mass. Now, a weighted average is not a regular average. You're accustomed to taking two numbers like these here, 12.0000 plus 13.00335. You're accustomed to taking these numbers here and dividing it by 2. That would be a regular average. That's not what we're talking about. That's assuming an equal percentage of each isotope, 50-50, instead of what we actually have. So in this case, when you take the weighted average, you have to factor in these different percentages. And what you do is move the decimal 2 places to the left and 2 places to the left here. And for each case, take that percentage and multiply it by its isotopic mass. So it's 0.9889 times the isotopic mass of the first plus 0.0111 times the isotopic mass of the second. And that's how you end up getting the weighted average atomic mass of this element, which is carbon. You'll notice too that what you end up calculating, the atomic mass that you calculate, the weighted average atomic mass, will be closest to the isotope with the greatest percentage. That makes sense mathematically, since the isotope with the greatest percentage, one that is 98.89 in this case, has the greater weight of that average. Or another way of saying it is, the 12.011 is closer to 12 than is 13.0035 because the 12 has a greater percentage of the isotopes. All right, we'll see questions on isotopes in the back. Not often asked to calculate the weighted average. You'll see it on a part 2 if it does occur. And most of the time, the isotopic questions are, if you ask to calculate a weighted average, it's just a mathematical setup. That's how they've been playing it recently. Otherwise, it's just a simple multiple choice that emphasizes the fact that isotopes are atoms of the same element that differ in the number of neutrons. Okay, now that we have isotopes down and we have our pen down, let's go a little bit further. And let's talk about where exactly are the electrons. In other words, the electron configuration. Again, this is information that you're going to find in the key The electron configuration of carbon is 2-4. What does that mean? That means that in the first orbit or shell of carbon, there are 2 electrons, 2 E's. Now, probably in elementary school, you were accustomed to drawing it as dots. All right. And here I've only given you parts of the shells. Typically in elementary school, you would draw it as orbits. The term orbit reminding you of how the planets orbit around the sun, the electrons orbit around the nucleus of an atom. This happens to be what we call the Bohr model of an atom, where you have the nucleus in the center and electrons orbiting at specific distances from the nucleus. All right. The electron configuration, once again, is the arrangement of electrons in the energy levels. I like energy levels, as you'll see why, or orbit shells, in an atom in the ground state. The ground state is the lowest or most stable state for that atom, the lowest energy state. Now, the electrons that are in the outermost energy level, drawing 4 dots here so you can relate to it better, would be called the valence electrons. So those numbers again, 2, 4, the electron configuration of carbon, are telling you the number of electrons in each of the 2 orbits. All right, and then the valence electrons, that's something you should remember. All right, because the valence electrons are the most important electrons. The valence electrons are the ones that are furthest from the nucleus, and they're the most important because the valence electrons will be involved in the chemical reactions of this element. So, valence electrons are the furthest out, the furthest away from the nucleus, and they're the most important. Carbon has 4 valence electrons. And being that they are the furthest away, the valence electrons are going to be the most energetic, because the further away an electron is from the nucleus, the more potential it has. All right, so as you increase the distance, or the greater the distance of an electron from the nucleus, the greater or the higher the energy of that electron. Now let's take a look here. In the ground state, meaning the lowest energy state, the most stable state, electrons fill the lowest available energy level, starting from the shell closest to the nucleus. So what that means is, when you come across an atom that has so many electrons, whatever the total happens to be, in the case of carbon, it happens to be 6 electrons, you don't place all 6 electrons in the first orbit. There's a certain number of electrons that can occupy any particular orbit. And when we fill in these orbits, or energy levels, we start with the one closest to the nucleus. So since the first one has a limit to complete it of 2, we place 2 electrons in the first orbit. And in the case of carbon, since there are 4 electrons remaining, the second orbit can hold a maximum of 8. We'll place those 4 electrons in the second orbit, giving us a total of 6. So the numbers are 2, 8, 18, 32 to complete the energy levels. And the numbers you can see very easily are given to you here, the configurations for the elements. Now, why is it that the first orbit can only hold 2, and the next 8 and 18, etc.? Well, when you do advanced studies on this, you'll understand it better when we start talking about a different model of the atom. For the time being, you're just going to have to go by the configuration that's listed here in the table and trust that that is the most stable configuration. Now, one more thing. There is a limit to the number of valence electrons that any element can have, and that maximum is 8. No element can have more than 8 valence electrons. There happens to be only one exception to that rule, which is platinum. All right, I think it's platinum. No, forgive me, palladium, Pd, element number 46. If you look in your periodic table there, you'll see that palladium has 18 valence electrons. But that's really besides the point, how to scope this course. So 8 is the magic number. I always remember it's 8 ball in the corner pocket. If you're a pool player, 8 is the magic number for valence electrons. Okay? Now, moving right along. At the bottom of page 6, what we have here are some illustrations that explain what you see when looking at the light that is emitted by an excited element through an instrument called a spectroscope. So what happens is that in this example here we have illustrated a hydrogen discharge tube, and you have high voltage. The electricity passes through the hydrogen gas, and this may have been demonstrated in class. And what happens is then that light that comes out of the hydrogen is channeled through a narrow slit in this instrument called the spectroscope, which then makes that light pass through a prism, and the prism, that glass prism, will do the job of separating that mixture of light into its colored components, because the light that's given off by an excited element is actually a mixture of colors. And so what you end up having is because it's coming through a narrow slit, you end up getting these lines projected on the background of the spectroscope, and they appear as brightly colored lines with dark spaces in between them. Now, unfortunately, in this diagram, which is just black and white, you really can't make out the color here. But I have a photograph of these spectral lines, which even in your review book, or most review books these days, they don't invest the money in giving you colored photographs. So let me show you what a photographic plate of this would look like. I'm going to come up close so you can see it better. And something like that. I hope you can make out the colors now. So those are brightly colored lines against a dark background. And that would be the bright line spectra of different elements. Okay, now explaining how this occurs is diagram B here. See, the light that we see from an excited element is actually due to the movement of electrons as they drop down to lower energy levels. So what first happens is the electrons in the atoms of these elements absorb heat or electricity, and that's why we had a high voltage source here. In lab, if you did flame tests where you took samples of different salts, metallic salts, and you heated them in a Bunsen burner, in that case you supplied heat energy. And so the electrons first move to an orbit that's further away from the nucleus in which they begin, and that's called the excited state. And then what happens is when those electrons return to the orbits that they came from, they end up emitting light. So, and that's what this is depicting right here. This squiggly line here is showing you an electron dropping down from the excited state down to the ground state, from a higher energy level to a lower energy level. And each line that appears, each spectral line on this background of the spectroscope corresponds to a specific amount of light energy. Now, since more than one electron in an atom can do this, you'll have more than one spectral line. Altogether, each of these spectral lines altogether give you a set called the BLS, the bright line spectrum of the specific element that you're exciting. And what I have here is a question from old Regents, something like it, where they had the bright line spectra of different elements side by side, so you could see that no two elements have the same bright line spectrum. And so you could identify the components of an unknown by simply matching up the lines. So in this example here, this line here, as you can see, matches up with this spectral line in helium. And then these two match up with helium and hydrogen. And this one here matches up again with helium, hydrogen, this one here, again, these two, finally, with hydrogen. So since these lines match up only with the spectral lines in hydrogen and helium, then you would conclude that the unknown contains
hydrogen and helium. Again, one more time. Electrons emit light when they jump from a higher to a lower energy level. All right, it's from higher to lower. Another way of saying that is when they go from the excited state back to the ground state. And you can think of the analogy here very simply. Think of a pen or a marker. Now that marker, if I plant it on the table, which is you're seeing there, that marker is not going to move. Now, because gravity is holding it on the top of this table. Now, in order for this marker to move, I have to put energy into it. In a sense, you could say the marker has to absorb energy. So the marker has gone from the ground to an excited state by absorbing energy. And then when the marker drops, it makes sound. So as it drops down to the ground, the marker makes sound. We have an energy transition, in this case, from mechanical energy to sound energy by way of the marker. In the case of bright line spectra, the energy conversion is from heat or electricity to light by way of an electron. And if you think of it that way, it's much easier to understand. Okay, we'll be turning to the next page. This is the bottom of page 6. You can take a break if you like, or just continue with me.